Hello. Today we're going to be proving a lemma. Let's try it. Okay. Which states let G of D be all real numbers, be continuous at Y, which is in D, with G of Y not equaling 0, then there are delta greater than 0 and alpha greater than 0 such that if the absolute value of x minus y is less than delta and x is in D, then the absolute value of g of x is greater than or equal to alpha. So this is what we're gonna, so now is the proof. So let's make alpha equal to the absolute value of g of y over 2, which would be greater than 0. So there is a delta greater than 0 such that for absolute value of x minus y less than theta, with x being in the domain, we have the absolute value of g of x minus g of y is less than alpha. Thus, the absolute value of g of x is greater than or equal to the absolute value of g of y minus the absolute value of g of x minus g of y, and all of that is greater than the absolute value of g of y minus alpha, which equals g absolute value of g of y over 2, which equals alpha. Now, suppose g is continuous at y and g of y does not equal 0. By lemma 3.3, there are deltas that are greater than 0 and alpha is greater than 0, such that for the absolute value of x minus y, which is less than delta, and x being in the domain, then the absolute value of g of x is greater than or equal to alpha. Sorry, that looks like A, but it's alpha. Okay, I fixed it. Okay, now when we make epsilon be greater than 0, let epsilon prime equal alpha times g, absolute value of g of y, with times epsilon, which is greater than 0. And there's delta greater than 0 such that for absolute value of x minus y, which is less than delta prime, and x is in the domain, absolute value of g of x minus g of y is less than epsilon prime. Now, let delta double prime equal the minimum of delta prime and delta, where double prime is greater than 0. And for the absolute value of x minus y, which is less than delta double prime, with x being in the domain, the absolute value of 1 over g of x minus 1 over g of y equals absolute value of g of y minus g of x over g of x, g of y, which is all less than epsilon prime over alpha times absolute value of g of y, which is equal to epsilon. So by theorem 3.2, the third part, f of g is continuous. Now let's flip it over and do another one. Oh wait, wrong way. Oh, okay, well, we'll flip it over and do another one. Okay. So now, the next thing we're going to try to find out is if f is in the domain. If f of d is all real numbers and g of d prime is all real numbers, with the infimum being less than d prime, where f is continuous at y, which is in the domain, and g, which is continuous at f of y, then g of f is continuous at y. Now here how we're going to prove it. Now choose an epsilon bigger than 0, and there's a delta 1 which is bigger than 0, such that if the absolute value of y minus f of y is less than delta and y is in d prime, then the absolute value of g of y minus g of f of y is less than epsilon. Now there is a delta 2 which is greater than 0, such that if the absolute value of x minus y is less than delta 2 and x is in the domain, then the absolute value of f of x minus f of y is less than delta 1. And since the infimum is less than delta prime, if x minus y is less than delta 2 and x is in the domain, then f of x equals epsilon epsilon times delta prime, and f of y equals epsilon delta prime, and absolute value of f x minus f of y is less than delta 1. Hence, absolute value of g of f of x minus absolute value of g of f of y equals absolute value of g of f of x minus g of f of y, which which is less than epsilon, and therefore GOF is continuous at y. I hope this helped you. Yeah, have a good day.